Thanks a lot, Katja, and thanks for the invitation. So we met with Katja at AIP, and I agreed to give a talk about this topic and say something about the proofs as well. So this is based on joint work with Rakesh and Mikko Salo. So let me begin by giving a little bit of context. So let me start by recalling what is the sort of the more classical Calderón problem, and then I will move to this Lorentzian version. So I'm interested in this geometric version of the Calderón problem, where we look at a harmonic function u on a Riemannian manifold with boundary, and f is the boundary value of u, and then Dirichlet-Neumann map is defined by taking f to the corresponding normal derivative on the boundary. And the classical Calderón problem is then to find the geometry or the Riemannian metric tensor G given the Dirichlet-Neumann map lambda. Well, this problem is very much open, and in fact, well, if we we should actually state the problem a little bit more precisely. So this is, of course, a geometric problem. It doesn't care about the system of coordinates that we choose. So in fact, the problem should be viewed as if two Dirichlet-Neumann maps are the same for metrics G and G naught, then a solution would be, or the problem what we want to show is that G is isometric to G naught. So in other words, it is associated to G naught via a diffeomorphism that fixes the boundary. So this problem is solved only in some cases where let's say the anisotropic part of the geometry has some let's say real analyticity in it. So if the whole metric is real analytic, then it was solved by Lassas and Ullmann, and there is also this result where we have this sort of conformal rescaling of a product metric. So here this anisotropic structure here in the parentheses doesn't depend at all in this t coordinate here, the direction. So it's real analytic in t. And this result is only recovering the conformal factor C here. So it's in a fixed conformal class. So what I was worried about for a while is that for this type of inverse problems, for geometric inverse problems for PDEs, there seemed to be some hidden real analytic assumption, like all these positive results have some sort of real analytic feature here. And well, one point in this talk is that we can get around this. We can have some results where there is no real analytic features. Okay, but let's move on to the wave equation. And so this Riemannian version of the problem seems intractable at the moment. At least I don't have any idea how to attack it. But if you go to the hyperbolic version, there are more tools that you can use, and there are stronger results by now. So this is one version of one way of going to the hyperbolic case. You just take a product of your previous Riemannian manifold with a time interval, and then look at the wave equation in this product geometry. Now you get a similar problem, so you still want to recover the geometry, and you just associate this wave equation a Dirichlet-Neumann map in a very similar manner as for this elliptic case. So you just look at you have a source on the sort of lateral boundary, and then again the map gives you the normal derivative on the same lateral boundary. As this is a wave equation, we also add this vanishing initial conditions, which I simply denote like u vanishing for negative times. So here is also a picture. So in my pictures, time is typically the vertical axis, and the horizontal directions are the space directions. And the inverse problem is formulated in the same way. So given the Dirichlet-Neumann map, now this hyperbolic version, recover the Riemannian metric. And this problem is completely solved by using the boundary control method that goes back to Belishev's original idea, and the geometric version is by Belishev and Kurilev, and there are many other contributions that I'm not going to go into the details now. All right, but I would like to argue that this is not the right hyperbolic analog of the Calderón problem, and in fact, a simple dimension count should convince one of this. So if we think about the number of variables in this Riemannian metric, well, it's the same as the spatial dimension. Let's call that n. And if I look at the Calderón problem, the Dirichlet-Neumann map, well, it's an operator, but if I count the number of variables in the sense that I look at the Schwarz kernel of this operator, I realize that it is just like in boundary rigidity, so the dimension is 2 times the dimension of the boundary, because this is an operator mapping functions on the boundary to functions on the same boundary. So in other words, this depends on 2n minus 2 variables. Whereas if you think how many variables this corresponding or the hyperbolic analog depends, well, now you have also the time dimension. So, and this is defined on boundary cross time, so that's n variables. So you could argue that this depends on, or the Schwarz kernel depends on 2 times n variables, but there is this translation invariance in time, so you should actually subtract 1, but still the dimensions don't match. So this is really not, in my opinion, the right analog. And we really need to go to some like proper Lorentzian formulation of a hyperbolic inverse problem to get the analog of Calderón problem. And this leads me to this definition of the wave operator on a Lorentzian manifold. So now let's consider, and I'm going to not be on a manifold for this talk to keep things simple and explain our new result. So it's in this setting. So we have a Lorentzian metric on just on this space, like 1 plus n dimensional Cartesian space, and this is a smooth function on that space, matrix valued, and the signature of this symmetric matrix is like 1 negative eigenvalue, and the rest are positive. And then we can define the canonical wave operator on the Lorentzian manifold, which is given by this formula. It is exactly the same formula as you would have for the Laplace-Beltrami operator on a Riemannian manifold. But now, okay, so you need to view this determinant as actually absolute value of the determinant, and because this has this indefinite signature, this resulting operator is a hyperbolic operator rather than an elliptic, as you would have in the Riemannian case. So a simple example is that if your Lorentzian metric is just the Minkowski metric, so it's just the line element in time and in space, but here we have negative sign. So in other words, it's this diagonal matrix with entries -1 and then 1s. Then the wave operator is just the usual wave operator, the classical wave operator, constant coefficients. But in general, of course, for this wave operator, the Cauchy problem is always well defined. But if you have some more complicated Lorentzian metric, this Cauchy problem here might not be solvable. And one abstraction, for instance, is that if there are time loops, so if there are some paths that somehow go all the time sort of forward in time, but then they are closed, so there is some sort of like time travel. It's possible to travel back in time on the Lorentzian manifold, then this Cauchy problem might not be well posed. And it's very typical, let's say, if you look at the literature in general relativity, for instance, to impose this global hyperbolicity condition on your Lorentzian metric that guarantees that the Cauchy problem is well posed. And so what does it say? So this manifold is globally hyperbolic if there is so-called Cauchy temporal function. There is a smooth function from the space to real numbers such that it's differential. So this is like the derivative in space and time is time-like with respect to this Lorentzian metric, meaning that when you plug in this vector given by the derivative of the exterior derivative, you get something negative, strictly negative. And then moreover, the levels of these functions should be what is called Cauchy hypersurfaces, though this means that all causal paths, all paths, sort of physical paths where matter or light can move, must intersect each of these hypersurfaces exactly once. Okay, so this is very standard notion, and it is as I said already required for in order to have a good direct theory for this wave equation. So it very much makes sense to assume this if you want to solve inverse problems for the wave equation in some Lorentzian manifold. Okay, so we are going to now make an assumption throughout the talk that all the geometries are globally hyperbolic. So this tau here should be then viewed as the sort of the time coordinate, if you want. It gives a global notion of time. And now with this, I can formulate what I call the Lorentzian Calderón problem. So this is now, in my opinion, the right analog of the Riemannian Calderón problem. So I'm going to state this in a little bit specific setting. That is the setting where I'm going to formulate the main result. So so let's look at just like some ball, well, it could be just a Euclidean unit ball, for instance, in Rn. And then we assume that a globally hyperbolic Lorentzian metric is the Minkowski metric outside this cylinder whose base is this ball. This, I could of course formulate this problem in a more general way, but for one, so one good thing that this assumption now guarantees is that the lateral boundary here is time-like, and it guarantees that this problem formulated here has, I mean, it's well posed. This has a unique solution. So this boundary, so in parallel, this boundary value here makes sense. And then I can define again the Dirichlet-Neumann map, so that it again takes the lateral boundary value to the normal derivative. And now the Lorentzian Calderón problem simply reads, given the Dirichlet-Neumann map, recover the metric tensor as we would expect. Okay. So now for this problem, we do have the right dimensions. So this is again supporting the fact that this classical Calderón problem and Lorentzian Calderón problem should be viewed as analog of each other. So my convention is that the spacetime always has n+1 variables, but if I just rename that to m, I see that the dimensions in unknown and data behave in the same way in these two Calderón problems. Okay. So this Lorentzian Calderón problem is also very much open, but we can say a bit more about it than the Riemannian case. So there are some very classical results that basically are in the context of this Gelfand problem. So if the Lorentzian metric has this product structure, then this is the Gelfand problem because you sort of factor out one sort of unknown. So there is translation invariance in time, so your dimension in the unknown drops by 1. And you can go a little bit beyond the product structure if the metric is real analytic in time. So this is a result by Eskin. These are based on boundary control method. And we can go also to some cases where there are no real analytic features if we assume certain curvature bounds, but then this result that we proved with Spiros Alexakis and Alif Faiz Mohammadi holds only in some fixed conformal class. So this is analogous to this result by Mikko and Günther and others that I mentioned earlier in relation to the Riemann inversion of the problem. But the good thing about this result is that it, for instance, holds for geometries that are close to Minkowski. So if I perturb Minkowski metric in a compact region, uh, I mean, I had a small perturbation there, then the curvature bound that we need holds. So this result is sort of robust against small smooth perturbations, unlike the previous two results. You can attack these problems in a fixed conformal class also using geometric optics. That's also quite classical. So it goes back to Stefanov in the Minkowski case, but that technique gives a reduction to inversion of the so-called light ray transform, which is integrating over light rays, and that transform is not known to be invertible except in certain, spaces that have some real analytic features, very similar to this two here, 2 points first points in the boundary control. Okay, there are also, of course, this recent or fairly recent idea of exploiting nonlinearity, and that allows you to solve some geometric inverse problems for nonlinear wave equations, even in just in the globally hyperbolic geometries, assuming nothing more. But those results require the generating equation, to be nonlinear. The inverse problem is always nonlinear. Okay. So now let me formulate the new result that I'm focusing on the talk. So it's a rigidity type result. So it says that we can have an arbitrary globally hyperbolic metric in this space, and the only assumption is that it is the Minkowski metric outside some compact region, and we assume that this compact region is inside a cylinder. Of course, you can always draw a cylinder around a compact region. And then if this unknown metric has the same Dirichlet-Neumann map as the Minkowski one, then in fact the unknown metric is the Minkowski metric up to a diffeomorphism that is fixing the exterior of the compact region. And so what is the strength of the result is that here this unknown metric can be completely arbitrary, and it certainly can be perturbed in a smooth and small way. Of course, the other metric then is very simple. It is the Minkowski metric. So we like to view this as an analog of this classical result by Gromov in the context of the boundary rigidity problem. So what is boundary rigidity? Well, you have a Riemannian manifold with boundary, compact MG, and dg is the distance function on the manifold, and then you're given distances between all pairs of points x and y on the boundary of the manifold. In other words, you're given the distance function restricted on the boundary, and you want to recover g, the Riemannian metric. And Gromov's classical result says that if the distance is on the boundary, so this means that the distances restricted on the boundary are the same, then the unknown metric is actually just the diffeomorphic copy of the Euclidean metric. So this was proven in the 80s, and now we know more about this problem due to Pestov and Ullmann in 2D and Stefanov, Ullmann, and Vasi in 3 and higher D. So under certain quite natural geometric conditions, this problem can be solved. So in some sense, in this Lorentzian Calderón problem, we know about as much as it was known about this boundary rigidity problem in the 80s. And hopefully, in the coming years, we can solve this Lorentzian Calderón problem under similar assumptions as these results by Günther and others. Right. But what I want to focus on today, so I was running quite fast with this sort of introduction and context because I want to have time to say something about the proof, and this is what I really promised to Katja. So I'm going to tell something about the proof, but only in the case when the metric is of this product form. So there is some Riemannian metric G, and then you just take a product with the time. But somehow this allows me still to explain the main ideas of the proof without going into too much technicalities. So it's not actually very different in the general case. There are a couple of steps in the proof. I'm going to tell more or less how these steps work, except for the third one, which is the most complicated. So I'm going to gloss over that. But let's now get to the business. So our starting point is that two Dirichlet-Neumann maps are the same. I'm going to pass from these Dirichlet-Neumann maps first to certain data set that I call plane wave data. So first let's have a look at what I mean by plane waves. So first, if you adjust in the Minkowski space and you fix a direction and, okay, so I actually deleted this shift parameter without, so I'll explain what this S is. But okay, so fix a unit vector, omega, in space. And then if h is the Heaviside function, this function u here obtained from the Heaviside function satisfies the Minkowski wave equation. And this Heaviside function, of course, the standard Heaviside function jumps from 0 to 1 at the origin, but you can maybe shift the origin by some number if you wish. And in fact, in this picture, where here is the space-time picture, this function u is 1 here on the gray area and 0 on the white area. And I guess here I've actually shifted a little bit because this jump between 0 and 1 doesn't go through origin. So include this shift in some, sort of implicitly here in H. But I don't want to clutter the notation with that shift. You could shift things up and down if you wish. And if I just look at what happens in the space, so here this dashed region is the cylinder of interest where the metric in principle could change. Of course, here I'm assuming that it's Minkowski throughout, so it's just the wave just goes through nicely here. The cylinder, I mean, nothing happens, nothing. Well, I mean, this interface, this plane where this function u jumps is just indeed a plane. And if I look at the sort of the wavefronts, or some sort of like snapshots of this function at fixed times and plot things in space, then the the function jumps over a plane or a line as in this picture, and then this plane has normal vector omega. And again, this circle here depicts the region where in principle the metric could change. And now if I really indeed let it change, then I get what I call distorted plane wave. So it is a solution now to this perturbed wave equation, where G can be different from Minkowski in the cylinder. And it is just obtained by solving this wave equation with initial data, if you wish, coinciding with the Minkowski plane wave. So for small times, the wave hasn't reached the cylinder, so this is solving also this perturbed wave equation. And then when time propagates, it goes through the cylinder, it might become distorted. And in space-time, it looks like this. So this interface here starts to wiggle, and in space only, again the interface also can wiggle. Okay, so now the first step is to show that if the two Dirichlet maps coincide, then this distorted plane wave actually coincides with the Minkowski plane wave outside the cylinder. So the picture looks like this. So there can be some wiggling here inside the cylinder, but then when it comes out, it just the interface is again straight, and it's sort of continuing along the same plane. I was planning to write the proof here, but that doesn't seem to be possible. So let's try to reproduce the picture here first. So I have this cylinder. Oops, and then the plane wave is coming in, and it may wiggle here, and then it comes out. Okay, so so this is our starting point. So U is is like the Minkowski wave plane wave for small times, and then it satisfies the wave equation. So let's record also that. So this is capital U, and for small times, it's the Minkowski plane wave. Now the idea is to take some time level here, so that the Minkowski wave hasn't entered yet into the cylinder. So this is some time level tau equals tau 0, and and we consider a solution U to let's say small case U to wave equation now inside the cylinder only. So this equation we wanted to hold in the whole R1 plus N, but this is going to hold only inside the cylinder. And then I'm going to put boundary condition. So on the boundary of the cylinder, this is the Minkowski plane wave, and then it should vanish here when in this region when the Minkowski plane wave hasn't entered the cylinder yet. Okay, so this is a well-posed problem for the wave equation. You can just go ahead and solve it. And then because the Dirichlet-Neumann maps agree, so lambda is lambda Minkowski, so it implies that the normal derivative of U on the boundary is also going to be the normal derivative of the Minkowski plane wave on the boundary, because for the Minkowski case, the solution to this equation is just a plane wave. Now I'm going to define another function v, which is defined in a piecewise manner. So it's going to be U inside. It's U when you're inside the cylinder, and it's going to be just the Minkowski plane wave when you are outside the cylinder. And now you see this U has the same boundary condition with the Minkowski plane wave, and it also has the same normal derivative with the Minkowski plane wave. Sorry, so I should say on the boundary, right? Whereas this is defined as U inside and as U min outside. Sorry about that. So it has the same boundary condition and also the same normal derivative, which means that when you glue things together, you will get a solution to the wave equation. And you see outside, it also works because G is the Minkowski metric outside. And now, if we think about how, so U is 0 here inside, and so is the Minkowski plane wave, because I mean in this region below this time level. So we see that initially, in fact, this glued thing satisfies the same initial condition as that capital U there. So for small times, this is just the Minkowski. So we have these two equations valid, which means that in fact, so for small times, this is should say, maybe be a little bit careful with my notation. So so this equation here and this equation here, they are the same, and that equation has a unique solution, which means that V is U, and in particular it implies that sorry, I need a little bit more space here. V outside the cylinder is which by definition is U min, and then this is the same as capital U outside the cylinder. So that's what I wanted to show. I wanted to show that this perturbed plane wave is the same as Minkowski outside the cylinder. So that finishes the proof of my first lemma. Okay, so let's go back to the slides. So I proved this lemma now. Okay, then I'm going to basically forget this Dirichlet-Neumann map and just look at these plane waves. And in fact, I could reformulate the whole problem by using only these plane waves. And it turns out that I need only these plane waves for finite number of directions, which actually allows us to show that the same result holds for formally determined amount of data, meaning that the dimension of the unknown is the same as the dimension of the data, but I'm not going to go into the details in that. Okay, so the second step, we need to consider this object that we call single plane wave scattering relation. So first, let me recall what is the usual scattering relation for a Riemannian manifold. So it is just a map that takes in a vector at some boundary point that points inside, then shoots a geodesic from to that direction, and then records the exit direction and point. So that the incoming direction is mapped to the outgoing direction, and that's the scattering relation. Now the single plane wave scattering relation is a bit like that, but we shoot now we take a plane here and shoot geodesics that are normal to the plane through the region, and then when they exit on the other side of the region, we record the points and directions. And if I think about this plane wave that goes through this region of interest, just by looking at its wavefront set outside of the region of interest, we can get these directions and this sort of surface here as a set. We don't get the mapping from this particular vector to that particular vector, but we get this, this curve here together with these normal vectors. And turns out that if I have this single plane wave scattering relation as a set in the sense of the previous lines, or in other words, I know the wavefront set of this plane wave outside the region of interest. And if that is the same as the corresponding object for the Euclidean metric, recall that I'm now looking at only this product case, then this unknown metric is simple in this direction, in the sense that these geodesics foliate the whole space smoothly. Or you can also express this by saying that if you look at this plane here, this initial plane, and you look at the boundary normal coordinates for that plane, they are actually global coordinates for the whole Rn. And so this is the step that I'm not going to explain. It's a little bit more technical than the other steps. You can also, totally, of course, follow the talk, just, assume this, and things still make sense. You can add an additional assumption in the unknown metric and say that it must be directionally simple. But, this is some sort of shortcut argument. The proof is some sort of shortcut argument in its heart, but it's, somewhat long. And it has also some analog in the boundary rigidity literature. So there is this result saying that if the distance functions of two metrics restricted on the boundary are the same, and if one of the metric is simple, then the other one must be also simple. So this theorem is similar to that. And I think this theorem you can find, for instance, in this fairly new book by Mikko Salo, Günther Ullmann, and Gabriel Patanen. But it's, it has existed in the literature for quite a while. All right. So moving on. So let's now accept that this unknown metric is directionally simple as the data coincides with the Euclidean case. And then it follows that this iconal equation here, where I look at the solution to, I look at the functions whose gradient has length 1 everywhere, and then somehow, well, sort of below this plane here, it is just x dot omega, then this equation has a smooth solution. And in fact, the solution is given by distance to the plane. Because if you think about the Euclidean case, this inner product with the normal vector, so recall that omega is this normal direction here, is a unit vector. So this is like the projection to the normal direction, which is the same thing as distance to this plane. And in this Riemannian case, this solution is also given by the distance to this plane, but of course it might not look as simple as this. But of course, what we are actually, anyway. So, and maybe it's also a good idea to realize that to have this example in mind, that if the metric is indeed Euclidean, then the unique solution to this equation is just this Euclidean distance. Okay. Yeah. So this is a classical result, but if you think about this this directional simplicity as saying that the boundary normal coordinates from this plane are global coordinates, then it's pretty clear that the distance function to this plane must be smooth, and then it's easy to check that it satisfies this this equation. Okay, so this is pretty simple, and it's also simple to say to notice this other consequence, namely that these distorted plane waves that are denoted by U, but if you recall that they are associated with particle metric and particle direction omega, these distorted plane waves actually can be written in this form, where you have some smooth function U as a factor here, and then you have heaviside that now jumps over this surface t equals phi of x. Now, why is this? Why the plane wave must look like this? Well, now this phi is a smooth distance to this plane, and just by finite speed of propagation, this plane wave, this distorted plane wave, must be zero if if you're sort of below this t equals to the distance to the plane, right? So this heaviside factor is basically explained by or at least the fact that you must be zero where the heaviside is zero is simply explained by the finite speed of propagation, whereas the smoothness of U is explained by propagation of singularities. So we know that this distorted plane wave has initially it has heaviside type singularity, and Herman's theorem on propagation of singularities tells us exactly how the singularity must propagate, and it's easy to derive from that it must be propagating like it is heaviside. So the singularity is no stronger than heaviside, and that then immediately gives the representation, because then we are just having something smooth happening on the region where the function is not vanishing, and where we know that there are no singularities by propagation of singularities theorem. Okay, so that's this step. That was fairly simple. Now I want to show that the distorted plane waves having this form actually allows me to construct a diffeomorphism, and that then will be the diffeomorphism in the statement of the theorem. And the first thing is to show that the smooth factor here that came from the previous argument is actually identically 1. Of course, in the Minkowski case, that smooth factor must be, I mean, it is 1. Okay, so there is this lemma. So if the distorted plane wave is like the Minkowski plane wave outside the cylinder, then U must be 1. And moreover, this solution to the diagonal equation, this distance function here, must be actually harmonic. Okay, so the lemma begins by a simple computation. So we know that this U here satisfies the wave equation. So that's the first step here. And then you just compute how the wave operator acts on this product here. And there will be basically 3 types of terms. Terms where you hit U only, terms where you hit once in U and once in H, and then terms where you hit twice in H. But in fact, the terms where you hit twice in H will vanish because this phi satisfies the diagonal equation. So there we use the fact that phi satisfies the diagonal equation, and then the rest of the terms look like this. So this term is easy. So there is this heavy side. I have just it is evaluated at the same point. It's evaluated at t minus phi of x. So I just hide it here. But then the wave operator has hit U, and then there is some derivative of heavy side, which is of course delta times something smooth here. And this derivative of heavy side, which is delta, is just of course living on this interface only. So if you're above the interface, you will see only the second term here, which then implies that, and as this is 0, it implies that this U must satisfy the wave equation in the gray area. And somehow, but U is below in the white area is totally irrelevant because that's not really that's killed off by this edge anyway. So we see that U satisfies the wave equation. That's the first observation. Here I haven't told you what is this Z. Well, it's a vector field. I don't really care what, I mean, you can easily compute what it is, but it's totally irrelevant because I'm going to use this fact here to show that U is identically 1, and then this term will go away. And as this term has already vanished, what I see here is that this phi must or Laplace of phi must be 0 on the interface here. And then I shift this interface up and down. So this is where the shift parameter comes into play that I have hidden in the notation. So I can shift things up and down and sort of sweep the whole space, and then this will be 0 everywhere. So that's somehow then the second second fact here. So what really remains to be shown is that U is identically 1. And again, let me move on here, and I need to redraw the picture. So I have the cylinder here, and let me make it quite large in time. And then there is this plane wave. It wiggles a bit, and then it comes out, and it's straight. And we already know that this U is 1 here outside the cylinder because there this capital U needs to be the same as Minkowski U, and for Minkowski, the small case U is 1. And from here we know that U satisfies the wave equation. Okay, and then what we will do is we will just do unique continuation, because you see, if I have constant function 1, it satisfies the wave equation. So I do unique continuation here, something like, I don't know, maybe like this. And I see that this U is 1 here. And in particular, there is some sort of time slice here where U is 1 and its time derivative is 0. And then I simply solve the wave equation from that initial condition. So u is 1, dt of u is 0 in this cylinder all the way up to this characteristic surface here. And that will tell me that u must be 1 here, which is what I wanted to show. So that's then the proof of this lemma. Okay. So then this will be this will lead to conclusion. So I still need to show that there is this diffeomorphism um, and that this unknown metric is the Euclidean metric when I change coordinates with this diffeomorphism. So I'm just going to construct this diffeomorphism from solutions to the aconal equation, where the directions, you recall that I set the initial condition for this iconal equation with this formula. So now I let this direction omega run through the coordinate directions here, and I call those corresponding iconal solutions phi j. And then I also need to use at some point these sort of directions that are sort of diagonals between the coordinate axes. Okay, but in this diffeomorphism, only those coordinate directions will play a role. They will be the components of this map. And then what I claim is that when I go to these coordinates, the metric is the Euclidean one. And these two things are sort of proven at once. And let's see how it works. So I need to go here and let's have some more space. So let's consider. So this phi is now the solution to the iconal equation with this boundary condition phi for some very so initially it is one of these diagonals. So let's say directions j and k, and then you just normalize. And then here in this region, I can then rewrite this as phi j plus phi k divided by, sorry, somehow, so this is omega times that. Sorry, this is x times that. So this is my omega, right? So this is my omega. X times omega. This is x times, sorry, this is just this combination, just using the linearity of this inner product here. Okay, but now all these functions here are harmonic. So this is harmonic, and so are these. And then as this equation here holds for in some region, I can use unique continuation to conclude that this same relation holds everywhere. So this is unique continuation. So we get that phi is phi j plus phi k divided by square root of 2 everywhere. Okay. And then, to see that these somehow give these are orthogonal in the derivatives of these phi j's are orthogonal in G, we can just compute. So now we use the fact that the diagonal equation holds. So this first of all is an diagonal solution, and then I just use this equation here. So I expand. So this is 1/2, and then d phi j plus d phi k squared, and then I expand the square, so I get 1/2. And there is one square here for this one, and this is also satisfying the diagonal equation. So it's like 1 for that, 1 for the other one, and then the cross term, which is 2 times g d phi j d phi k, like this. Now those two two things cancel with that one, and then I will see that G d phi j d phi k is indeed 0, which is the first part of the lemma, because, well, I mean, this is like the off-diagonal bit for the lemma, and for the diagonal, it's just using the fact that this phi j and phi j's are solutions to the diagonal equation. So it in particular shows that this derivative of f, the differential of f, is going to be injective, because all the columns here, the derivatives of these columns are linearly independent by this first part. And then to see that this f is a global diffeomorphism, we need to work just a little bit more, and we get it using this Hadamard's global inverse function theorem, which says that, if you have this local, if it's locally diffeomorphism and it's a proper map, then it's actually global diffeomorphism. And it's not very hard to show that this is a proper map, but I don't have time to do that. So let me end here, and I'm happy to answer any questions that you may have. Thanks.
Thank you very much, Lauri, for the very nice talk. Are there any questions or comments, please? Please feel free to unmute yourself. Any questions or comments, please?
Okay, I have a question.
Yes.
Here, Jianliang. Okay, so a delta function need all the direction of plane wave to be reconstructed. Why here you just need to have finite number of plane wave to get all the singularity correct?
Right. So this is only a unique result, and in particular, it's only like rigidity result, right? So it's probably not very stable. So if you're asking, I'm not claiming that I can recover all, let's say, singularities of the metric or something like that. If this is the question, I'm not sure if I understood correctly.
So maybe Rakesh can say something.
Sure. So let me see. So you asked the question in your chat was, why didn't you use the delta function? Am I correct?
Yes.
Is that the question?
That's right.
Yeah. So, okay. Now, if you're working with the Riemannian metric problem, so which the metric is independent of time, then whether you use the heavy side of the delta function, it doesn't matter because you can get one from the other.
Okay, just differentiate. Yeah, okay.
Right. But if you're doing the Lorentzian metric problem where the thing depends on time, then our proof is really for the Heaviside function. And also the other thing is that, if you use a delta function, then if you do the progressing wave expansion, then the principal term is a delta, and then you go to the next order term. So you're going to be using the second term will have the information, not the first term in some sense. So it makes it harder. You want to just tackle the first term when you're doing velocity problems.
Yeah.
So that's why we use the heavy side.
Okay. Okay.
So for the t-independent case, it doesn't matter. But for the Lorentzian case, it does matter. So a proof is for the heavy side. We really want to work with the first term in the expansion rather than the second term.
Yeah. Okay. So now I actually
Usually
understood the
speaking
question.
that. Okay. Now, second question which you asked, which was about if you use only a finite number of waves, do you expect stability?
Yeah.
Right? So, the question is the finitely determined, formally determined problem, is there stability? And the answer is that actually for the metric case, we are doing some work here. There is stability for certain families of Riemannian metrics from just a finite number. So like the formally determined problem with plane wave sources, we can get stability under certain conditions.
Okay.
Right.
So,
Right.
So,
Yeah, maybe I'll add to that. So yeah, so in fact, I mean, once you have enough many directions, you sort of there are no, at least no microlocal abstractions, right?
Mm-hmm.
So yeah, so
so my okay, my intuition is that okay, whether there's such a kind of finite number of plane wave will help us in terms of computation, because that means you just need to sample the object from finite number of directions. That will save you a lot of effort in measurement, right?
Right. No, it's very much so. Yeah. The thing is that, so if you look at a Riemannian metric, it has, it's symmetric. So it has n plus 1 over 2 coefficients, different coefficients. Right. So now, of course, you can only, if you can only recover it up to diffeomorphism, you can subtract n. So loosely speaking, you have n times n minus 1 over 2 different coefficients to be determined.
Okay.
Right. And so roughly we have used roughly something like that many directions.
Okay. Yeah. Thanks.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Lauri, for the wonderful talk. Thank you very much, everyone, for coming. Thank you so much.
thank you.